Hello friends, good afternoon and welcome to the EduSite network. Our topic of discussion today is carboxylic acids, and this is part of our ongoing series on chemical reactivity and mechanisms. And friends, today the subject expert is going to talk about things like what are carboxylic acids, how to prepare them, and I would like to introduce our subject expert, Dr. Vandana, Assistant Professor, Department of Chemistry, Dayal Singh College, University of Delhi. With this brief introduction, I would like to welcome ma'am and also request her to begin our today's lecture.
Thank you so much, ma'am. Good evening, everyone. Today's topic for this chemical reactivity and mechanism series is carboxylic acids. We will tell you about what are the carboxylic acid and how can we prepare by different method carboxylic acids. What are carboxylic acid? A carbonyl group and hydroxyl group. So we can say organic compound that contain the carboxyl group, carboxylic acids. So carboxylic group consists of a carbonyl group C double bond O and a hydroxyl group OH, all directly bonded to each other, hence the name carboxyl. The carboxylic group possess unique property that are different from those of the carbonyl group present in aldehydes and ketones, which we have discussed in last series of the lecture, and the hydroxyl group present in alcohols. This is due to the resonance interaction between pi electrons of the carbonyl group and an unshared pair of electrons on oxygen atom of the hydroxyl group. There are 4 electrons delocalized over the 2 oxygen atoms and the carbonyl group. These are the resonating structure of carboxylic group. You can see how these are possible by the probability of pi electron when shifted towards the more electronegative oxygen atom carbonyl group, and you can see the major contribution and minor contribution and the resonance hybrid of these 3 resonating structure of carboxylic acid. So the carboxylic group behaves as separate functional group which characterize the carboxylic acids, the acidity of which is due to the proton releasing ability of the carboxylic group. Carboxylic hydrogen is partially electron deficient due to electron withdrawing effect of the carbonyl group which is attached to the hydroxyl group. Carboxylic group may be classified as aliphatic or aromatic depending upon the group attached to the carboxylic group. The carboxylic acids are also classified as mono, di or tri carboxylic acid depending upon the carboxylic group attached to the other group. Dicarboxylic acid and tricarboxylic acid contain 2 and 3 groups respectively, and the carboxylic acid may also contain other functional group. There are the other examples. You can see the examples. Propionic acid, it is an aliphatic monocarboxylic acid. Cyclohexane carboxylic acid, alicyclic monocarboxylic acid, benzoic acid, an aromatic because phenyl group is there. Succinic acid, it is a dicarboxylic acid as 2 carboxylic group are there. Crotonic acid, it is because double bond is there, so we can say it is unsaturated acid. Lactic acid because one more hydroxyl group is there, it is a hydroxy acid. And pyruvic acid, a keto acid. So these are the examples with another functional group. Saturated aliphatic monocarboxylic acid, open chain saturated monocarboxylic acid are those which contain a carboxylic group attached to an alkyl group or an hydrogen atom. Hence, they may be represented by formula RCOOH, where R is an alkyl group or hydrogen atom. So they constitute a homologous series having a general molecular formula CnH2nO2. It is oftenly represented as CnH2n plus 1 hydrocarbon plus COOH functional group to show the presence of carboxylic group. Monocarboxylic acid containing unbranched hydrocarbon chain, which are oftenly known as fatty acid because many of them were obtained from the hydrolysis of animal fats or vegetable oils. This is from Greek word aliphatos, means fats. Nomenclature of carboxylic acid in IUPAC. The parent name of a saturated aliphatic monocarboxylic acid is derived from the name of alkane corresponding to the longest chain containing the carboxylic group. So we have to look the longest chain of the compound, and by replacing the ending E by suffix oic acid, The names of the substituent are prefixed to the parent name in alphabetically order to give the complete name. Unbranched carboxylic acids are simply named as alkanoic acids. The numbering of the parent carbon chain begins at the carboxyl carbon. The common names are derived from the Greek or Latin names of the natural sources from which the acids were originally isolated. These names have an ending ic acid. Here are the examples. You can see the table of some unbranched acids. First of all is HCOOH. Its IUPAC name is methanoic acid, whereas its common name is formic acid, derived from the natural source ants, that is formica. Next one is ethanoic acid, CH3COOH, common name is acetic acid, and it derived from the vinegar acetum. Next one is CH3CH2COOH, propanoic acid, we can say common name propionic acid, and it is also a first fatty acid. It is derived from fat, the name from protos, pion is equal to fat, means it is fat. CH3CH2CH2OH, butanoic acid, N-butyric acid, it is derived from butter. Next one is pentanoic acid, common name is N-valeric acid and derived from valerian root. Next one is hexanoic acid, its common name is caproic acid, which derives from goat's fat. Other examples are here, 2-methyl propanoic acid, its common name isobutyric acid, 3-methyl butanoic acid, isovaleric acid, and 2,2-dimethyl propanoic acid, pyvallic acid, trimethyl acetic acid. Now about the structure of carboxylic acid. The carbon atom and the 2 oxygen atom in carboxylic group all are sp2 hybridized. The carboxylic carbon atom forms 2 sigma bonds with 2 oxygen atoms separately by sp2 linear overlapping. It also forms another sigma bond with either a hydrogen atom by an sp2 1s linear overlap or an sp3 hybridized carbon atom by sp3 linear overlap. The OH, a bond is formed by sp2 1s linear overlapping. How it overlaps? You can see in the figure that it is a orbital picture of acetic acid and its resonance structure. You can see how the sp2 hybridization overlapping is possible to form 2 sigma bond, and there is another sigma bond formed by the sp2 orbital of oxygen with 1s orbital of hydrogen, and another sigma bond is formed by sp3 hybridization of carbon and 1s orbital of hydrogen. So you can see the resonance in acetic acid, how sigma bond is formed, how pi bond is formed, and how the localized pi bonding is formed. You can see also the delocalization of pi bond. Thus the carboxylic group is planar around the carboxylic carbon atom and the hydroxyl hydrogen lies in this plane. So oxygen carbonyl, carbon carbonyl, hydrogen carbonyl and carbon carbonyl oxygen or hydrogen carbonyl oxygen bond angles around the carboxylic carbon atom are approximately 120 degree. The carboxylic carbon atom forms a pi bond with non-hydroxylic oxygen atom by a pp lateral overlap. Thus the carbon oxygen double bond consists of a sigma bond and a pi bond. The oxygen atom of this carbonyl group contains 2 unshared pair of electrons accommodated in its 2 remaining sp2 orbitals. The hydroxylic oxygen atom contains 2 unshared pair of electrons, 1 pair accommodated in sp2 orbital and another in p orbital. You can see the different geometric parameters for formic acid and acetic acid. Different bond lengths and bond angles you can see in the formic acid and acetic acid. This doubly bonded occupied p orbital overlaps laterally with an pi bond orbital of carbonyl to some extent, leading to a delocalized pi bond in which pi bond character in carbonyl is greater than that in carbon to hydroxyl. The entire process of bonding in carboxyl group is shown in figure. We have already seen the geometric parameters we have already discussed. It may be noted that carbonyl bond length in carboxylic acids are slightly longer than that in aldehydes and ketone. This is due to the resonance in carboxylic acids. Isomers of carboxylic acid alkanoin having the general formula alkanoic CnH2nO2. These are the isomers for C2H4O2, 1 acetic acid, 2 methyl formate, 2 hydroxyethanol, and other 3 are unstable. Acyclic isomers for the molecular formula C3H6O2 are propanoic acid, methyl ethanoate, ethyl methanoate, and 3-hydroxypropanol. These are the cyclic isomers for the molecular formula C3H6O2. First one is cis-cyclopropane 1,2-diol. Next one is trans-cyclopropane 1,2-diol. Third, cyclopropane 1,1-diol. 2,3-epoxypropane 1-ol. 2-methoxyoxyrane, and others are some unstable structure you can see, and with 3-hydroxyoxetane and 1,3-dioxylane. Another isomers for the molecular formula C4H8O2 are butanoic acid, 2-methylpropanoic acid, methyl propanoate, and there are other 3 isomers possible are ethyl ethanoate, propyl methanoate, 1-methyl ethyl methanoate. Isomers with the acids and esters having molecular formula C5H10O2 are pentanoic acid, 2-methylbutanoic acid, 3-methylbutanoic acid, 2,2-dimethylpropanoic acid, methyl butanoate, methyl 2-methylpropanoate, ethyl propanoate, propyl ethanoate, 1-methyl ethyl ethanoate, and others 4 are also there. So, these are the possible isomers for acids and esters. How to prepare carboxylic acid? First of all, we can prepare the carboxylic acid by the oxidation of primary alcohols and aldehydes. Primary alcohols and aldehydes on oxidation with either potassium dichromate in dilute H2SO4, sulfuric acid, or potassium permanganate KMnO4 in acidic or alkaline medium yields the corresponding carboxylic acids. Primary alcohols are oxidized first to aldehydes and then to carboxylic acids. You can see how the primary alcohols react with potassium dichromate and sulfuric acid to give the alcohols, and with aldehyde it also gives the carboxylic acids. These are the other examples. Propane 1-ol when react with potassium dichromate in H2SO4 and with the heat propanol first form, then it is oxidized to propanoic acid. Next example is furan 2-carbaldehyde, or we can also say it is furfural when oxidized with potassium dichromate in H2SO4 will give you furan 2-carboxylic acid, or the common name is furoic acid. With KMnO4 potassium permanganate and KOH potassium hydroxide, potassium salt of carboxylic acids are formed with manganese dioxide and water molecule. There are the other examples. Butane 1-ol when react with potassium permanganate and KOH first of all oxidized to butanol, then potassium butanoate, and which on hydrolysis will give you butanoic acid. Next example is benzyl alcohol. What is benzyl group? C6H5CH2. It when oxidized with KMnO4 first of all gives you benzaldehyde, and then it will give you potassium benzoate, which on acidification will give you benzoic acid, the corresponding carboxylic acid. In the laboratory, aldehydes can be conveniently oxidized to carboxylic acid with silver oxide in ammonical solution. It is also known as Tollens reagent or a slurry of silver oxide in dilute sodium hydroxide solution. This is a milder oxidizing agent, and unlike potassium dichromate and potassium permanganate does not affect carbon-carbon double bond and triple bond present in the initial compound. Other examples are with silver oxide and ammonical hydroxide, trans-crotonaldehyde will give you trans-crotonic acid, and cyclohex 3-ene carbonaldehyde will give you cyclohex 3-ene carboxylic acid. Next reaction is haloform reaction, or we can say oxidation of methyl ketones. Methyl ketones on hitting with halogen, for example chlorine, bromine or iodine, in dilute sodium hydroxide yield sodium salt of carboxylic acids containing one carbon less than the starting ketones. Haloform is formed as a co-product, hence the name haloform reaction. The carbon-carbon double bond and triple bond are not affected in this oxidation. So, you can see the example how the oxidation of methyl ketones. Methyl ketones means when a methyl group is attached to the ketones. Here is the example of tertiary butyl methyl ketone when reacts with iodine and sodium hydroxide will give you first of all sodium salt, and then after acidification it will give you triethyl acetic acid, or we can also say pyruvate acid. Next example is 4-methyl pent 3-ene 2-one or macetyl oxide when reacts with chlorine NaOH and with heat will give you 3-methyl but 2-enoic acid. Another example with acetophenone, it will react with bromine NaOH and with the heat will give you benzoic acid. Next reaction in this series is oxidation of alkenes. How can we prepare carboxylic acid from alkene? Oxidation of symmetrical alkenes. Symmetrical means when the groups attached to the double bond are symmetrical, like here you can see RCH double bond CHR, and when there is a plane of symmetry, and terminal alkenes of the type RCH double bond CH2 with alkaline potassium permanganate gives carboxylate salts, which on acidification gives carboxylic acids. So, you can see here we are taking the symmetrical alkenes, it can be cis, it can be trans. When react with potassium permanganate, first of all will give you potassium salt of carboxylate, carboxylic acid. There are the examples. First of all we are taking the but 2-ene will give you ethanoic acid, and 3-methyl but 1-ene will give you methyl propanoic acid. Stilbene will give you benzoic acid. Ozonolysis of the alkenes of the type RCH double bond CHR and RCH double bond RCH2 yields carboxylic acid. So, you can see how ozonolysis form. First of all ozonide is formed, and which after hydrolysis will give you the corresponding carboxylic acid. So, first of all we are taking the examples of CH3 CH double bond CH3 symmetrical alkene will give you the 2 molecules of acetic acid, and terminal alkene will give you the corresponding carboxylic acid. Next preparation for carboxylic acid is hydrolysis of nitriles. What are nitriles? RCN, cyanide compound. Nitriles are hydrolyzed to corresponding carboxylic acid by boiling with either dilute mineral acid. What are mineral acid? These are the acid which are available in lab, like HCl, like H2SO4, like HNO3. These are the dilute mineral acid or dilute alkali. In either case the initial product is an amide which is further hydrolyzed to carboxylic acid. You can see in the reaction how nitrile first of all converted to amide and then carboxylic acid after hydrolysis. Another example, nitriles are conveniently prepared from primary alkyl halide by SN2 bimolecular substitution nucleophilic reaction with KCN or NaCN, potassium cyanide or sodium cyanide. Hence, carboxylic acid can be prepared from alkyl halide 1 degree, not 2 degree and 3 degree. So, we can prepare these only by 1 degree and secondary and tertiary will not produce. By conversion of the nitriles followed by hydrolysis, the carboxylic acid so obtained contain, this is the important point, we must notify one more carbon atom than the starting alkyl halides. So, if you want to increase the chain, you can take the example of this preparations. Thus, the method has been advantage of increasing the length of the carbon chain. Here is the example how toluene converted to phenyl acetic acid. First of all, it is chlorinated by chlorine, then react with potassium cyanide. This chlorine atom will substitute by cyano group by SN2 mechanism, and then hydrolysis, and after heating it we will get the phenyl acetic acid, means one carbon extra with the starting material. Next preparation for the carboxylic acid is carbonation of Grignard reagent. We know what are the Grignard reagent, these are the RMGX. The reaction of Grignard reagent with carbon dioxide is often the method of choice for preparing a carboxylic acid. The reaction is carried out by bubbling dry carbon dioxide gas into a solution of Grignard reagent in dry ether. You must be noted, whenever we take the Grignard reagent, dry ether is substitute, is the additional word, or by pouring a solution of the Grignard reagent in dry ether or THF, tetrahydrofuran, onto crushed solid carbon dioxide, and we can also say dry ice. The addition product is hello magnesium carboxylate salt is then decomposed with the dilute mineral acid to give carboxylic acid. Here are the example how the Grignard reagent first of all give you addition product and then hydrolysis will give you acetic acid. First example is methyl magnesium iodide with the carbon dioxide, and after addition product will get formed, then it on hydrolysis will give you acetic acid. Another example is bromobenzene, which will gives you benzoic acid. The intermediate addition product by Grignard reagent is phenyl magnesium bromide. Next example is 2-chloro-2-methyl propane, or we can also say tertiary butyl chloride. First of all give you addition product, then after reaction with carbon dioxide and acidification will give you 2,2-dimethyl propanoic acid or pivellic acid. Grignard synthesis provide an excellent method for converting alkyl halides into carboxylic acid containing one more carbon atom than present in the starting alkyl halide. Thus, it is useful for extending a carbon chain by one carbon atom. This method is more useful than nitrile hydrolysis method, which we have just 1 minute before we have discussed, because it is not very sensitive to the steric hindrance. It works well with primary, secondary, tertiary, alkyl, allyl, benzyl, vinyl and aryl halides, provided they do not contain such reactions groups are incompatible with the Grignard reagents, such as here are the example hydroxyl, carboxylic, sulfonic, amine, thiol, acetylene or carbonyl group. Next preparation for carboxylic group is from hydrolysis of trihalides. Hydrolysis of 1,1,1 trihalides with aqueous alkali yields carboxylate salts. Carboxylic acids are liberated from the salts by treatment with dilute mineral acids. So, here is the example with chloroform with potassium hydroxide. First of all give you potassium salt of carboxylic acid, and this on acidification hydrolysis will give you formic acid. Another example is toluene when reacts with chlorine in excess. First of all will form the benzo trichloride, then potassium benzoate, salt is formed, and after acidification hydrolysis will give you benzoic acid. Another preparation for carboxylic is the COOH reaction or hydrocarboxylation of alkenes. Alkenes are heated with carbon monoxide and steam under pressure at 300 to 400 degrees Celsius in the presence of phosphoric acid, that is H3PO4, to form carboxylic acid. The addition of hydrogen atom and a carboxylic group across the double bond occurs in the accordance with the Markovnikov rule. So, here are the example for ethylene and propylene. The products are propionic acid and isobutyric acid respectively. You can see the mechanism, how the mechanism proceed. First of all, proton adds to the carbon and then carbon monoxide add, and then after hydrolysis you will get the carboxylic group. Next is the reaction of sodium alkoxide with carbon monoxide. Sodium alkoxide, what are sodium alkoxide? RONA. When heated with carbon monoxide under pressure form carboxylate salt, and after acidification will give you carboxylic acid. You can see the example of sodium methoxide, first of all give you sodium acetate, and then after acidification will give you acetic acid. Next preparation is hydrolysis of ester. What are esters? You are very much aware of it. What are ester? RCOOH or R dash. Esters of carboxylic acids on heating with dilute aqueous acid or alkali yield carboxylic acid and alcohols. You can see in the reaction how the product carboxylic acid and alcohols are formed. Acid catalyzed hydrolysis is slow and is reversible and does not proceed to completion. Alkali promoted hydrolysis is the almost irreversible, faster and gives almost quantitative yield of product. For this reason, alkali promoted hydrolysis is preferred. So you can see how the ethyl propionate ester will give you propanoic acid after acidification. First is the acid hydrolysis, and next example is the alkali hydrolysis with NaOH. When methyl benzoate hydrolyze with NaOH, first of all give you sodium benzoate and then benzoic acid. This method is of little preparative value because esters are generally obtained from carboxylic acid themselves. However, it is useful for isolation of carboxylic acid which occur in nature in the form of fats or oils. Since soaps are prepared by alkaline hydrolysis of fats and alkaline hydrolysis of ester is called saponification. Next synthesis is malonic ester synthesis. In this method, diethyl malonate is first treated with sodium ethoxide to form diethyl sodium malolate, and it is nucleophilic reagent and react with primary alkyl halide by SN2 mechanism to form diethyl alpha alkyl malonate, and the subsequent hydrolysis will give you alpha alkyl malonic acid which decarboxylate and 150 to 200 degrees Celsius to give monocarboxylic acid. Malonic acid itself decarboxylate at 140 to 150 degrees Celsius to form acetic acid. So you can see how diethyl malonate will form you alkanoic acid. First of all, it reacts with sodium ethoxide to form diethyl sodium malonate, then alkylation will take place, you will get the diethyl alpha alkyl malonate, and after alkaline hydrolysis you will get the alpha alkyl malonic ester, and then after decarboxylation you will get the product alkanoic acid. So, it is very synthetically very important reaction. This acid so produced contains 2 more carbon atoms. We have studied the 2 synthesis by Grignard reagent and by nitrile synthesis, that 1 more carbon chain will increase, but here you can increase the 2 more carbon atom than the parent alkyl halide. So, it is very important. You can see the example how malonic acid will convert it to acetic acid and diethyl malonate will convert it to butanoic acid. First of all salt is formed, and then after alkaline hydrolysis decarboxylation will get the butanoic acid. Side chain oxidation of alkyl benzenes. Alkyl benzene means when an alkyl group is attached to benzene ring. Here is the example, toluene. Aromatic acids can be obtained by the side chain oxidation of alkyl benzene with strong oxidizing agent such as alkaline potassium permanganate or chromic acid, and the alkyl benzene must possesses at least 1 hydrogen at the benzylic position. So, toluene acid first of all will give you potassium benzoate and then benzoic acid. Propyl benzene first of all give you benzoic acid, will give you benzoic acid and acetic acid. Para-nitrotoluene will give you salt and then para-nitrobenzoic acid. Next point is the physical properties of carboxylic acids. First we will discuss the physical state and odor. Formic acid, acetic acid, propionic acids are colorless, pungent smelling liquid. Alkanoic acid containing 4 to 9 carbon atoms are colorless, oily liquid having unpleasant smell. The acids containing 10 or more carbon atoms are waxy solids. So they are almost odorless because of their low volatility. Boiling point. The boiling point of carboxylic acid are considerably higher than those of hydrocarbons, alkyl halides, alcohols, ethers, aldehydes, ketones and amines. It means amines and esters. It means carboxylic acid have higher boiling point than these functional groups which have already stated. This is because carboxylic acid forms strong intermolecular hydrogen bonds, stronger than those in alcohols and other functional group. Carboxylic acid forms strong hydrogen bonds because their oxygen and hydrogen bonds are more strongly polarized than those in alcohols, and the oxygen atom of carbonyl group with which they have hydrogen bond is better electron donor and more electronegative than the oxygen atom of alcoholic OH group. We have already learnt that hydroxyl and oxygen hydrogen bond in alcohol are stronger than in amines, than hydrogen bonds in amines. You can see the dimer of carboxylic acid and you can see the hydrogen bonding in carboxylic group. In the solid and liquid states, a pair of carboxylic acid molecules are held together as a cyclic dimer by 2 hydrogen bonds. The dimeric structure persists also in the solution of non-polar aprotic solvent. What are aprotic solvent? Aprotic solvents are the solvents in which there is no proton to donate after dissociation. Although we have proton in benzene, but we cannot dissociate simply. So aprotic solvent example is benzene and to some extent even in vapor state. The boiling point of a straight chain alkanoic acid gradually increases with increase in molecular mass. Melting point. Carboxylic acids have much higher melting point than compounds of most other classes with comparable molecular mass. The melting points of straight chain alkanoic acid do not increase in a regular manner. The melting point change in manner so that melting point of an acid with an even number of carbon atom is higher than those of the preceding and succeeding homologous with odd number of carbon atoms. Thus, the melting points show alternation from one member to the next. This is due to the closer packing of even carbon acid molecules, as you can see in the structure, even carbon acid molecules and odd carbon acid molecules. This is due to the closer packing of even carbon acid molecules in the crystal lattice compared to that of the odd carbon acid molecules. It happens because in even carbon acid molecules, the terminal methyl group and carboxyl group are situated on opposite side. You can see in the even carbon acid molecules that methyl group and carboxylic group are on opposite side. When they are on opposite side of the zigzag carbon atom, this arrangement permits the molecule to fit together more closely in the crystal lattice, thereby increasing their intermolecular attraction. So you can see the even carbon acid molecules and the odd carbon acid molecules in which the methyl group and carboxylic group are on the same side and they can less closely fit in the crystal lattice. Next point is the solubility. We know solubility is the formation of hydrogen bond. Like dissolves likes. The first 4 alkanoic acid, that is formic acid, acetic acid, propionoic acid, butyric acid, are completely miscible with water in all proportions. The solubility of carboxylic acid in water is due to their intermolecular hydrogen bonding with water. You can see the hydrogen bonding between a carboxylic acid and water. As the chain length increases, the solubility of carboxylic acid in water decreases because the increase in hydrophobic repulsion of non-polar hydrocarbon part of the molecule. Carboxylic acids are also soluble in organic solvents such as alcohol, ether, benzene, chloroform and carbon tetrachloride. The reason for the acidity of carboxylic acid, it is very important point to discuss the acidity of carboxylic acid is due to the resonance stabilization of carboxylate ion. How it form? The acidity of carboxylic acid can be attributed to the greater resonance stabilization of the carboxylate ion, or we can say conjugate base, compared to that of the unionized carboxylic acid molecules. So, you can see the structure of carboxylic acid and carboxylate ion, and in the carboxylic acid the resonance is small and in the carboxylate the resonance is large, and you can also see the resonance hybrid. The resonance in carboxylate ion involves two equivalent resonating structure which contribute to resonance equally. As a result, the charge density on oxygen is reduced efficiently and the carboxylate ion is highly stabilized. In the case of resonance of un-ionized carboxylic acid, one of the resonating structures involves charge separation and is therefore a minor contribution. As a result, it is less stable structure. Hence, the resonance in unionized acid molecule is not as stabilizing as that in the carboxylate ion, because these are the equivalent resonating structure. The gain in the stability in passing to a carboxylate promotes the ionization of carboxylic acids. How to compare the acidity of alcohols and carboxylic acids? As we have already stated that carboxylic acids are much more acidic than alcohols. Example, acetic acid is about 10 to power 11 times more acidic than ethanol. The reason is that the alkoxide ion, or we can say conjugate bases of alcohols, are less stable than the carboxylate ion. The conjugate bases of carboxylic acids, the negative charge in alkoxide ion is contrast to carboxylate ion is localized on the singly oxygen atom because the alkoxide ion cannot exhibit resonance. So, it is the important point because ethoxide ion does not have any resonance. This is why the alkoxide ions are less stable than the carboxylate ion, because carboxylate ion have two resonating structure which are equivalent to each other. Then thus an aqueous solution of an alcohol is neutral while testing to litmus paper than that of carboxylic ion, which changes a blue litmus paper red. We are also looking this test in our laboratories. So, you can see the ethoxide ion derived from ethanol, it is a conjugate base of ethanol, and acetate ion from acetic acid. Comparison is acidities of phenol and carboxylic acid. Phenol is acidic because the resonance stabilization of phenoxide ion, or we can say conjugate base of phenol, is greater than that of the phenol. The resonance is phenol is involved three charge separated resonating structure of low stability. For this reason, phenol has a low resonance stabilization. You can see the structure. And for the resonance in phenoxide ion, on the other hand, involves two major contribution in which the negative charge is placed on more electronegative oxygen atom. You can see in the resonating structure. Moreover, the negative charge is localized over ortho and para positions of benzene ring and three other contributors. The combined effect result in increased stability of phenoxide ion related to undissociated phenol. So, you can see the resonance structure of phenol. The lone pair of electron of hydroxyl group will attracted by the benzene group, and there are the resonating structure as compared to the resonance structure of phenoxide ion. These are more stable because you can see in the two structure the negative charge resides on the oxygen atom. Carboxylic acids are much more acidic than phenol because the resonance stabilization of a carboxylate ion is greater than that of the phenoxide ion. The negative charge in carboxylate ion is delocalized over 2 oxygen atom of 2 equivalent resonance structure. Hence, the stabilization is high. On the other hand, in the resonance of phenoxide ion, all the contributors are not equivalent. You can see in the phenoxide ion, then among 5 possible resonating structure, 2 of the resonating structures reside the negative charge on oxygen atom, while the other 3 not. They will reside the negative a charge on carbon atom, among 2 on ortho position and among 1 is on para position. So, moreover in 3 of the resonating structures, the negative charge is placed on the less electronegative carbon atoms. So, this is one of the reason. Therefore, the resonance stabilization of phenoxide ion is less than that of the carboxylate ion. In the carboxylate ion, you can see the resonance structure of carboxylate ion, both the carboxylate ion are equivalent in structure. Phenols are about 1,000,000 times more acidic than alcohols. This is because the phenoxide ion is resonance stabilized while the alkoxide ion has no resonance stabilization. You can see this is the alkoxide ethoxide ion and there is no resonance. Phenols are about 1,000,000 times more acidic than alcohols, and this is because the phenoxide ion is resonance stabilized while the alkoxide ion has no resonance stabilization and are thus less stable than the phenoxide ion. So, here is the order, the acidity of alcohols, phenols and carboxylic acid. Alcohols are less stable than phenols and phenols are less acidic than carboxylic acid. Effect of substituents on acidity of carboxylic acids. Any factor which stabilizes the carboxylate ion or the conjugate basis of carboxylic acid more than that it stabilizes the carboxylic acid should increase the acidity. And on the other hand, any factor which destabilizes the carboxylate ion will decrease the acidity of carboxylic acid. So, we can also say electron releasing group decrease the acidity while electron withdrawing group will increase the acidity. First, we will discuss the effect of electron releasing substituent on acidity. In formic acid, hydrogen atom is there attached to the carboxylic group, so we are not taking it in consideration. In acetic acid, however, the methyl group is electron releasing relative to the hydrogen atom. So, plus I effect of this methyl group will intensify the negative charge on oxygen atom of the carboxylate ion and consequently destabilize the acetate ion. We have already stated that this negative charge if intensify will decrease the acidity, if it is increases the acidity will also increase. Since the acetate ion is less stable than the formate ion, acetic acid is a weaker acid than formic acid. So, you can see the formate ion, acetate ion, how the acetate ion destabilized by plus I effect of the methyl group. As the size of the alkyl group bonded to carboxylic group increases, the plus I effect also increases and the acidity will decreases. The plus I effect of alkyl group increase in the order, you can see the order. Hence, acidity decrease in the following order: formic acid, acetic acid, and then propanoic acid, butyric acid and others. Benzoic acid is a stronger acid than formic acid, but a weaker acid than acetic acid. Why? Because the phenyl group in benzoic acid is less electron releasing than the methyl group in acetic acid. Since the sp2 carbon of the phenyl group is more electronegative than the sp3 carbon of methyl group. So, order of acidity is formic acid is the greater acidic compound than phenyl carboxylic acid and then acetic acid. Effect of electron withdrawing group substituent on acidity. Electron withdrawing group, for example, halogen hydroxyl group alkoxy group, amine, thiol, SR, NO2, cyano group, carbonyl group, carboxylic group, ester group and others, when present in the carbon chain of alkanoic acid, increase the acidity as compared to the corresponding unsubstituted acid. This is reason, the reason is that they stabilize the carboxylate anion. We have already stated that any factor which stabilize the carboxylate anion will increase the acidity by dispersing the negative charge on the oxygen atom in carboxylate ion. For example, chloroacetic acid is a stronger acid than acetic acid. This is because the minus I effect of chlorine which stabilizes the chloroacetate ion, while the plus I effect of methyl group destabilizes the acetate ion. So, here are the structure of chloroacetate ion and acetate ion. The minus I effect due to the chlorine atom stabilizes the conjugate carboxylate ion, and in another acetate ion it is destabilized by plus I effect, that is by methyl group. Acidity increases as the electron withdrawing power of the substituent increases. The order of alpha haloacetic acid parallels the order of the electron negativities of the halogen atoms. You can see the order: fluorine is greater than chlorine, then bromine and then iodine. Greater the electronegativity of halogen atom, greater is the electron withdrawing, or we can say inductive effect, and greater is the stabilization of alpha haloacetate ion. So, here is the order of acidity with the different halogen atoms, with fluorine atom, with chlorine atom and with bromine atom. The value of Ka is also indicated, and the order of acidity for acetic acid and other groups are also given in this slide. Next is the acidity decrease with increased distance between electron withdrawing group and the carboxylic group. As the electron withdrawing substituent is moved along the chain away from the carboxylic group, its inductive effects falls off rapidly with increase in the distance. Hence, the stabilization of carboxylate ion decreases and consequently acidity will also decreases. You can see the examples of 2, 3 and 4 chlorobutanoic acid, and next is the acidity increase with increased number of electron withdrawing substituent at a particular position. As the number of electron withdrawing substituent increases, the electron withdrawing power of a group as a whole becomes greater than that of one such substituent. As the stability of carboxylate ion increases, and consequently the acidity will also increases. These are the examples with acetic acid, chloroacetic acid, dichloro and trichloroacetic acids. That is all about the preparations of carboxylic acid, and in this lecture the next important heading is the reactions of carboxylic acids, which we can categorize in 5 points. Number 1, reactions due to hydroxyl bond, OH bond. Next, nucleophilic acyl substitution reaction. Next, reactions involve decarboxylation, means removal of carbon dioxide, reduction reactions, or reactions involving alpha hydrogen reaction. In the next series of this lecture, chemical reactivity and mechanism, we will discuss the reactions of carboxylic acids and comparison with aldehydes and ketones. As we have discussed in the last lecture that aldehydes and ketones are giving nucleophilic addition reaction, and carboxylic acids give nucleophilic substitution reaction. Why these carboxylic acid give nucleophilic substitution reaction, we will discuss in the next coming lecture. So, thank you so much.
Thank you so much, ma'am, for this very interesting and informative lecture that we had today. Of course, the students would see this as an opportunity to learn a lot more, and there would be more discussion on this, of course, further. And with this, just a brief question I would like to ask, ma'am. So, if one wants to learn more about carboxylic acids, could you suggest the name of any book or any other source, or what are the things they could do to know more about carboxylic acids?
As far as about the carboxylic, I have taken all the preparations in my PPTs, but still if you want to, there are the number of books are there like Morrison Boyd, like Fenner, like Solomons, like Jerry March, like SM Mukherjee. Number of organic books are there, you can take data from there. Okay. And number of preparations are there with their mechanisms.
Okay, right. So the students can make use of these books. Otherwise, I think ma'am's lecture would be sufficient to learn about carboxylic acids. And just very briefly again, we have talked about carboxylic acids. Is it possible to use this as a area of research for probably MPhil or PhD? Is any kind of research happens on these things?
Definitely, if we can make the derivative of carboxylic acid, we have to go through the net first, that where these functional groups are used, and then we can modify the available compounds with their synthetic value or applicable value. First of all, we have to search that these compounds are used where. Then we can make the modified compounds of these compounds.
Right. So then you suggest that if a student probably at MSc level wants to take it up as a subject of research, yes, it is possible to go an in-depth study.
First of all, you have to survey the literature where, right, these compounds are already used. Then you can think of the modification of these compounds. Slight modification if you can do, they can better use in future.
Definitely. Thank you, ma'am.
Thank you so much.
Before we wrap up, I would like to just ask from what level do students start learning about carboxylic acids? Do they learn about this in school or just starting from graduation?
They first of all studying in the 11th and 12th level, and very few reactions are there. And in graduate level, you have to understood all the mechanism which happens in the preparations and the reactions of the carboxylic acids.
Right. So the brief kind of a knowledge begins from the very school itself. So of course, then one could go into a more in-depth study and take it as a specialization as one's study also increases and time progresses. So friends, this was all from us, our side today. As ma'am has already discussed carboxylic acids, what they are, and how to prepare carboxylic acids. So that was discussed today, and of course, we must thank ma'am once again for being associated with us, for sparing her valuable time. Thank you, ma'am.
Thank you so much.
And thank you, friends, for watching. Have a lovely day ahead. Take care.